Okay, hey everybody. So I just wanted to make this lecture video so you can have this as a potential resource as you are preparing for exams and whatnot. So let's get this screen sharing started over here. And we flip over. Okay. So this section is about passive transport. So we talked a little bit last time about the importance of plasma membranes and how it mediates what is coming in and out of the cell and why that is important for homeostasis or otherwise maintaining life, the chemical conditions under which metabolic processes have to occur. Okay, so this section is chapter 5, section 2 of your textbook. And so I'll throw this and make this an active link before I upload this to Canvas. So things that we want to make sure that we understand is how and why passive transport occurs. What's the difference and similarities between osmosis and diffusion? And then we have to talk about this term tonicity and how that is important to transport, because passive transport is all about the relative concentration between what's happening inside the cell and outside of the cell, and that's what tonicity is, and we'll get there. Okay, so plasma membranes are selectively permeable. Some stuff can come in and out of the cell, and other stuff has to stay where it is. So I put a picture of my two little border collie puppies here, and this little goofball Maggie here with her tongue sticking out really likes to find bones in the forest. So sometimes there'll be the carcass of a cow or an elk or something, and then she'll find the bones and she'll want to bring them into the house, but she is not allowed to do. However, the dogs can bring in bones that I purchased for them from the grocery store, right? So my front door then is acting as a selective agent to say this can come in, but that has to stay outside, because I don't want that forest bone in my house where I live and where my kids are and stuff. So that's a gross thing that stays outside. Okay, so that's kind of what's happening with the plasma membrane, is that it will allow some substances to come into the cell. It allows some substances to leave the cell, and vice versa. Okay. And so when we think about plasma membranes, we got to remember that the inside and the outside of the cell are not exactly symmetrical. They're not the same. And so from this image that I yoinked from your textbook, you guys can see that there's some of these proteins that pass all the way through the plasma membrane. There's some of these proteins that are stuck to the inside and are just interacting with the phospholipid bilayer and the aqueous solution and a little bit of the fatty acid tails, but they don't push all the way through. We've got some glycolipids, some glycoproteins, we've got some cholesterol hanging out in there. And it's not one for one, but what we see on the inside of the cell is different from what we see on the outside of the cell. And the easiest way to see this is to look at these peripheral membrane proteins that are attaching these cytoskeletal filaments. So these are in animal cells. This is what gives these filaments give the cells their structure. And so they're attached to these proteins that are embedded on the inside. And then one of the things that we see embedded on the outside are these glycolipids and glycoproteins that are used for cell communication, for recognition and stuff. Okay. So kind of having established that, we can start to talk about passive transport and active transport. Now, it kind of, the names imply the differences between these two. So both active transport and passive transport is moving stuff across that membrane, but passive transport does this without energy input from the cell. And the way that this mechanism works is that it's going from a high concentration down to a low concentration of whatever the thing is that we're talking about. And I'll give some examples here in just a little bit. Whereas active transport requires some energy input. This doesn't happen just automatically. The cell has to do some work for it. And the way that that work is energized is through this molecule called ATP that we keep talking about, but haven't really defined yet. So we'll talk about it in a little bit. So active transport requires energy input. Passive transport just kind of happens naturally without any energy input from the cell. Okay. The reason that the plasma membrane can be selectively permeable is because it's amphiphilic. And now this word might sound really scary and be really hard to understand, but if we're keeping a running track of root words, prefixes and suffixes that we've heard, so you've probably heard of amphibians before. And so this amphi, or maybe an amphitheater, this means dual, and the amphi is dual. Okay, so this is a dual loving thing. So these molecules, remember about phospholipids, they have a hydrophilic head that has a negative charge on one of those phosphates that makes it want to interact with water. We have the two fatty acid tails that are hydrophobic, and so they're trying to get away from the water, and that's why we see the phospholipid bilayer orient itself in this way, with the phospholipid heads on the outside and then the fatty acid tails pointing down to each other. So stuff that can move through this amphiphilic membrane are nonpolar substances. So these are other things that are fat soluble, okay? Other things that are hydrophobic. Also things that can pass through are low molecular weight, and that's just a fancy way to say that they're very small molecules. Molecular weight is just that, remember when we talked about the molecular mass of the thing, which is based on how many protons and neutrons it has. Well, if you add up all the atoms that make up that molecule, you can get its molecular weight. So if it has a small molecular weight, it's probably a little small, tiny molecule. If it has a large molecular weight, there's a lot of atoms and it's a big molecule. So things that are small can pass through easily, even if they're polar. So like, for example, water molecules can pass through the plasma membrane only because they're small. Even though they're polar, because they're small, they can still do it. They just don't do it very well. And so we see actually specialized proteins that will help them. But anyway, some examples of things that can move through the plasma membrane passively are fat soluble vitamins such as vitamin A, D, E, and K. Carbon dioxide and oxygen are both very small molecules, and so it's easy for them to kind of fit through the cracks and get in and out of the plasma membrane really easily, which is good because that's what we need to do when we get to the chapter about metabolism. You'll see why, oh yeah, it's a good thing those guys are small so they can get in and out of the plasma membrane easily. Okay, stuff that doesn't move through easily requires active transport, and these are things that are polar molecules. So a lot of our amino acids are polar. Let's see, things that are hydrophilic, so like sugar molecules, they don't pass through very easily. Ions that have a strong charge don't, even though they're small, but because they have that strong charge, they don't really pass through easily. And so we have to have a way to get those things through the membrane. Okay. And then just this quick little sidebar, because we're going to introduce some terminology that I don't think we've covered in class yet. So When we talk about solutions, what we're talking about is some junk dissolved in some other junk. Okay, so the solvent is usually a liquid that does the dissolving. So like water, if we're talking about salt water, then water would be the solvent. And then the solute, that's the thing that is dissolved. So in the case of salt water, that would be the salt, or sugar water, it would be the sugar. It's the thing that dissociates to become mixed up in that solution. So the cytoplasm is a solution. So I like to call cytoplasm cell juice. It's just this gooey stuff that's inside the plasma membrane, and it's kind of this stuff that everything floats around in. When we talk about ribosomes and lysosomes and nuclei and Golgi apparatus and all that crap that we're going to cover, it's floating around in this cell juice that's contained within the plasma membrane. And that's our cytoplasm. All right, so now that we've got that figured out, we can start talking about this process of diffusion. Diffusion is one of the mechanisms for passive transport. It allows our solute, the thing that is dissolved in the crap, to move from a high concentration, where it's really packed in tight, to a low concentration. And it's always moving from high to low. So if you kind of think about, like I've been to Collins one time. So, when I was there, drunk white girl dancing on the dance floor, there was a high concentration of people. And after a while, I got kind of done with that. And I wanted to diffuse and go toward an area where there was a lower concentration of people. And so maybe that's something that you guys can relate to, of being in a crowded area. You kind of want to give yourself a little bit of space. And that's kind of the same concept that's going on here, is that we're going from a high concentration to kind of a more spread out low concentration. And that concentration gradient, this is going from this little diagram of a high concentration. That's a high energy environment. Those molecules are pushed up against each other, and they're kind of bumping against each other, and they're repelling each other. And then as they kind of get more spread out, a little bit more room, the potential energy lowers a little bit. And so cells actually take advantage of that potential energy gradient to help them power their cellular processes. Okay, so that's pretty much what I just said, that the potential energy dissipates as the gradient, the concentration gradient, equalizes. And now we can get to this idea that once it equalizes, we get to this state that we call equilibrium. And so as these sugar, let's say call them sugar molecules, let's use these as an example, that we've got a bunch of sugar molecules dissolved in this fluid. When you make your Jell-O and you dump the packet into the hot water, you have an area of really high concentration, and those molecules are bumping around and they're moving into each other, and they're and they're kind of spreading out. They're using those random movements to help them spread out. So when we reach equilibrium, stuff is still moving around, but it's still but there's the same amount of movement coming in as coming out. And so the amount of movement is equal, but there's still movement going on. And so I use this image of a faucet filling up a tank, but then there's another faucet that's emptying it. And so if these two faucets are sending out water at the same rate, then the level of water in this tank is going to stay at an equal level. So we can say that it's at equilibrium, even though we have an input, but we have an equal amount of output. Okay, so what are some things that can affect the rate of diffusion? Oop, I just lost my focus. Oh well. So things that can affect diffusion are how strong that concentration gradient is, how big the molecules that are doing those diffusing. So if there's a really strong concentration gradient, then diffusion is going to happen quickly at first and then slow down as we get closer to equilibrium. Large molecules are going to diffuse more slowly than small molecules because big things tend to move slower than little things. The temperature of the solvent is going to matter. So how fast are those water molecules moving around? If they're moving around faster, then we're going to see faster rate of diffusion because there's more things that are bonking into each other. And so they're spreading out faster than if they're slow and the molecules are moving slowly. The solvent density. So, are we talking about, water has pretty low density. So are we talking about another kind of fluid that has a higher density? Things are going to move slower in those denser solvents. Again, just because there's, if you try to move through the dance floor at Collins, there's a lot of people that are going to get in your way and you're going to have to move more slowly than if you were on a night when it's not very busy and there's not very many people there, and then you can move quickly, right? Just because there's not as much stuff getting in your way. So another thing that can affect the rate of diffusion is actually the plasma membrane itself. How thick is it? How much surface area is there? The more surface area there is, the more stuff can get through, but the thicker it is, the more time it has to take for them to get through. So a thin plasma membrane, diffusion can happen a lot faster than in a thick way. And then again, that kind of relates to the distance traveled. So how far do these solutes have to move in order to get to where they're going? This does actually limit cell size, because if you have some molecules that you're trying to diffuse out of the cell and it's taking a long time to get there, then that's going to interfere with the cellular processes. Okay, and so the three that we're going to test in our little lab today are the mass of the molecules diffusing by using different colors of food coloring, temperature, and then by just, saying we're going to have some boiling water, some room temperature water, and then some water that I've been keeping in the fridge so it's nice and cold. And then we have some solvent density where I've made a simple sugar to go with just plain water. And then you guys can probably think about some of these other ways that we could test some of these other factors using our food coloring method. Okay, so I'm going to stop here for now, and then I'll make another video about the rest of this.